Suppose we wanted to figure out the limit as x goes to 0 of the sine of x over e to the 2x minus 1. So I want to make sure I'm doing this right. Yeah. So the first thing you always try when asked to evaluate a limit is to do what?
Substitution.
Substitution. So let's actually plug in x equals 0 and see what we get. Well, we get the sine of 0 over e to the 2 times 0 minus 1. And we know the sine of 0 is?
0.
0. E to the 0 is what?
1.
So we got 1 minus 1, which is also 0. And so this is our indeterminate form. We don't know what's happening there. Now, if you think back to chapter 2, when we had indeterminate forms, we had a handful of tricks to help us with these things, right? We could try to factor things out, cancel things out, whatever. We had sine x over x as a special limit. We didn't really have any special limits with the exponentials. So at this point, we'd be kind of stuck, right? What do we do? Well, this is where L'Hopital comes into play. And the key idea behind L'Hopital, since it is, once again, an application of derivatives, is differentiability means local what? Differentiability means local
Linearity.
Linearity, right? If there's nothing else you take from this class going into the distant murky future, is that differentiable means things are locally linear. So I'm heading into 0, right? Both of these functions, sine and e to 2x minus 1, are differentiable at 0. So let's look at f of x equals sine of x. And let's take a look at the tangent line at x equals 0. So our tangent line formula, y equals f prime at 0 times x minus 0 plus f of 0. So let's see, f of x is sine of x. So what's the derivative of sine?
Cosine of x.
Cosine of x. So let's look at f of 0, f prime of 0, and f of 0 is what?
0.
And f prime of 0 is?
1.
1. So I put these together and I get my tangent line is y equals x. Okay. So this means that if x is approximately equal to 0, sine of x is going to be approximately equal to x. Right? That's what that means. And here it is, right? So there's the promised local linearity there. I filled the bird feeder yesterday, so that's what the cat is voicing, but hopefully that's not too distracting.
Can't even hear it.
Can't even hear it? Okay. Maybe it's in my head. Maybe that'll be the big joke at the end of all of this. I don't have any pets.
You can hear it in the recording, though, but not in actual WebEx.
That's wild, because I'm using the same mic.
Makes sense. I thought you said you're using a different mic for...
No, I fixed it.
Oh, okay.
It's the same mic now. Huh. All right, let's take a look at g of x equals e to the 2x minus 1. I'll do the same thing. What's the derivative of this one?
Uh, 2x e... Oh, sorry, 2e to the 2x.
2e to the 2x. Good. And so for the tangent line, once again, y equals the slope g prime of 0 times x minus 0 plus g of 0. G of 0 we know is 0. What's g prime of 0?
2.
2. So I put these together, I get y equals 2x. So if x is close to 0, then g of x, which is e to the 2x minus 1, oops, I'll put it this way, e to the 2x minus 1 is going to be approximately 2x. Right? So we'll show that. Boop. And so there's the local linearity for that function. Okay? So here's what L'Hopital's rule says. I'm taking the limit as x goes to 0 of sine x over e to the 2x minus 1. And so x is getting close to 0, right? It stands to reason, and I'll put a question mark there, it stands to reason when x is close to 0, I can approximate sine x by x. I can approximate e to the 2x by 2x. Now, this is still an indeterminate form, right? But what can I do with the x's here?
Factor.
Yeah.
Or cancel.
And what would I be left with then?
1/2.
1/2. Okay, 1/2. And so in other words, instead of looking at the ratio, right, of the red curve over the green curve as you go to 0, we'll look at the ratio of these two lines. And once again, the hand wavy justification is here, I'm close to 0 now, which is where the limit cares about. Can you tell the difference?
No.
No. All right. So this kind of gives rise to L'Hopital's rule.